We'll do a little bit more from section 4.3 now. In 4.3, we're looking at how derivatives affect a graph. And where I ended the last video was I had talked about the first derivative test. The first derivative test is really just the increasing and decreasing test. Okay, but in this chart that we can make, once we've determined where the function is increasing or decreasing, we can then be able to find or state local mins or maxes. Okay, so let's take a look at another example here. In this one, I want us to find the local max and min values for f of x equal 1/2 x minus sine x, and we'll have x ranging from 0 to 2 pi, okay, and that's an open interval. Well, I'm going to have to find my critical values and create this chart using the increasing and decreasing test. So f prime of x would be 1/2 minus cosine x. The critical values are the numbers that are going to return 0 from the derivative, or numbers that you can't plug into the derivative. So I'd want to set f prime of x equal to 0 and solve this equation here. If you add cosine x to both sides, cosine x equal 1/2. Well, cosine x is adjacent over hypotenuse. The adjacent side is 1 and the hypotenuse is 2. The opposite side would be root 3, and the angle that you'd be talking about would be pi over 3. Okay. Now, if I were to flip that triangle in quadrant 1 over into quadrant 4, that's going to affect the opposite side, which I don't care about for cosine x, right? Cosine x is adjacent over hypotenuse. The opposite side would be a negative. That doesn't affect anything. The adjacent side would still be 1 and the hypotenuse would still be 2. The angle that you would be describing there in quadrant 4 would be 5 pi over 3. If you flip that triangle either into quadrant 2 or quadrant 3, then the adjacent side would be a negative 1, and we don't want that. We need to be a positive 1. So now that I've got my critical values, I'm going to set those on the number line here, and of course I'm going 0 to 2 pi was the condition on x, and so that's going to split this table into 3 sections for me. Okay, I want to write interval, number chosen, value of f prime, and then the conclusion. That's basically the table template that I'd like you to use here when you're drawing your chart. And of course, in these problems, make sure that you have the chart shown. Okay, I'm going to be grading you on the chart and the work that you've shown there in getting the answers. All right, so my first interval is going to be representing all the numbers between 0 and pi over 3. And then the second group is going to be all the numbers that are between pi over 3 and 5 pi over 3. And then the third group is going to be all the numbers that are between 5 pi over 3 and 2 pi. We always want open intervals in the chart. Okay, no brackets. So now I'm going to choose any number I want. And of course, when you're using the chart, make sure that you're selecting nice values. You can select any number you want. It's just, make sure it's in the interval, and you got to do the calculation with that number. So ideally, it works well to do mental math calculations. If you can select nice values, and of course, in a problem like this, I'd want to select nice trig angles, for example, pi over 4 would be between 0 and pi over 3. And if I plug pi over 4 into the derivative, cosine pi over 4 would be 1 over root 2. Okay, 1 over root 2 would be roughly about 0.707 if you were to look at the decimal form. So I'm looking at 0.5 minus 0.707, that's negative 0.207, okay? And here'd be the exact form, of course. The fact that that's a negative means that I'll be decreasing on that part of the graph. So then the next group, I need a number between pi over 3 and 5 pi over 3. Pi is between those two numbers. And if you plug that into the derivative here, cosine pi is negative 1. 1/2 minus negative 1 would be 3/2. That's a positive, so that means that I'll be increasing on that part of the graph. And then if I select a number between 5 pi over 3 and 2 pi, 7 pi over 4 would be an angle to use there. And I plug that into the derivative. So cosine of pi over 4 is 1 over root 2. cosine of 7 pi over, well, 7 pi over 4, that just means I'm going to flip that triangle over into quadrant 4. That's going to affect the opposite side, which doesn't matter. Cosine of 7 pi over 4 is also going to be 1 over root 2. 1/2 minus 1 over root 2 is roughly negative 0.207. Okay? And so we're back decreasing again. Okay, we're decreasing, we're increasing, and then decreasing. So the fact that we are decreasing and then increasing, we're going to produce a local min at x equal pi over 3, and then increasing to decreasing, we're going to produce a local max at 5 pi over 3. Okay, now if I plug in pi over 3 into the function, here's my function, to get the output, I'm going to have 1/2 times pi over 3 is pi over 6, and then my sine of pi over 3 is root 3 over 2. Pi over 6 minus root 3 over 2 would be roughly negative 0.342 if you were to go nearest 3 digits. Okay, and if I'm sketching a graph, which they didn't ask me to do that in this problem, but we're going to be doing lots of curve sketching here coming up, so just to kind of get us in the routine of doing that, I have drawn a graph. And I'll need to know where to position these points here. Okay, so if I plug in 5 pi over 3, 1/2 times 5 pi over 3 would be 5 pi over 6, minus sine of 5 pi over 3. Okay, well, sine of pi over 3 is root 3 over 2. If you flip that triangle into quadrant 4, the opposite side would be a negative then, and so sine of 5 pi over 3 would be negative root 3 over 2. Okay, 5 pi over 6 minus a negative means you're adding root 3 over 2, and in decimal form I was getting roughly 3.48 if you go nearest 2 digits. Okay, I'm not super picky about the rounding, of course make sure that you're still using the approximation sign since there is rounding. Alright, we're going to have a local min at pi over 3, negative 0.342, and then we're going to have a local max at 5 pi over 3, 3.48. Go ahead and circle, that would be the answer there. Now if I were to sketch this curve, f of x, on the interval 0 to 2 pi, if x is 0, y would be 0, right? And so that point is not on the graph, right? I'm not including either one of these two endpoints here. If I plug in 2 pi, sine of 2 pi is 0. 1/2 times 2 pi is pi. Okay, pi is roughly 3.14, so here's the point 2 pi pi. That point is also not on the graph. Okay, now I've found the local min that was at pi over 3, and by the way, just the nature of the critical numbers here, I used a scale that moved in an increment of pi over 3 on the x-axis. So at pi over 3, come down to a height of negative 0.342, and that's going to be the local min on the graph. And then at 5 pi over 3, we'll come up to a height of 3.48, and we'll plot a point, and that's going to be the local max. Okay, now I'm decreasing from 0 to pi over 3, so the curve is going to be falling, and then I'm increasing on that middle section, so curve would be rising, and then I'm back decreasing again, so it's creating a hill there and falling back down and bumping into that open circle. Okay, so here would be just a quick rough sketch then of the graph of the function f of x. Of course, what I'm doing here is very handy information that I can use when I sketch the graph, right? I can find the peaks and the valleys, the mins and the maxes, where it's increasing and decreasing, and that's very useful, like I said. Okay, here's another example. Find the local extrema for g of x, which is x squared minus 4, the quantity to the 2/3 power. Okay, so I want to find the critical numbers, and I'm going to use the first derivative test. So g prime of x, that's be a chain rule. We're going to have 2/3 x squared minus 4 to the negative 1/3 times the derivative of x squared minus 4 is 2x. When you simplify that, we're going to have 4x divided by 3 times, it'd be the cubed root of x squared minus 4 to the 1/3, that's fine. Okay, and I'd want to set that equal to 0 and solve. If you multiply both sides by the denominator, then that'll clear out the fraction that we have on the left. 4x equals 0 means that x is 0. Now make sure that you get all of the critical numbers. Remember, a critical number is a number that is in the domain, and you plug it into the derivative, and is either going to return 0 or you can't plug it into the derivative. Okay? The domain of g is all real numbers. I can let x be anything here for g of x. Now with g prime, 2 and negative 2 are going to be a problem, right? Because I know I can't divide by 0. So 2 and negative 2 would also be critical values when I list the numbers. Now, again, make sure that you get all the critical numbers, because I'll have students only write 0, and they'll make this table here with only 2 columns where it should be 4 columns, and then that's going to lead to a wrong answer. Okay. Make sure you get all the critical numbers. So I've got my table set up, interval, number chosen, value of f prime, and then the conclusion. And I've arranged these numbers in order on the number line, and that's going to split the number line into 4 sections for me. Okay, and now I can select my test values here. So I need a number that is less than negative 2. I selected negative 3. Okay, plug that into g prime. You're going to have negative 12 divided by negative 3 squared is 9, minus 4 is 5. 5 to the 1/3 times 3, that's going to be a positive number. So you're going to have negative 12 divided by some positive number, that's going to be a negative. Negative 2.34 would be if you go to the calculator and enter that. So we're going to be decreasing on that part of the graph. How about if x is negative 1? Okay, I'm going to select that number for the next interval there. Okay, plug that in. We're going to have negative 4 divided by negative 1 squared is 1, minus 4 is negative 3. The cube root of negative 3 is a negative number. Times 3, that'd be a negative. Okay, so I'm going to have negative 4 divided by some negative number. Negative over negative is positive. I was getting 0.92 if you were to use the calculator. And that would mean that we're increasing on that part of the graph. Okay, now we need a number between 0 and 2. If we use 1, the only change from when we had selected negative 1 would be in the numerator. We're going to get 4 instead of negative 4, what it was. There's still going to be a negative number in the denominator if x is 1. 4 divided by a negative is negative. Negative 0.92 is what I was getting there, so we're going to be decreasing on that part of the graph. And number in the last section here, if I could use 3. So if x is 3, the only change from what it was when it was negative 3 there in the first group would be I'm going to have a positive 12, whereas it was a negative 12 from before. I'm going to still have a positive in the denominator. Okay, 3 times the cube root of 5 is what I get there. So 12 divided by 3 times the cube root of 5, that would be 2.34 roughly if you were to go nearest 2 digits. And so we're back increasing again. Okay, now I'm decreasing and then increasing. That's going to produce a local min. I'm increasing and then decreasing. That's going to be a local max. And then decreasing and increasing. That's going to be another local min. Let's state those points where we have the local extrema. So we're going to have a local max at x equals 0. And when x is 0, if you plug that into the function g of x, you're going to have negative 4 to the 2/3. Well, negative 4 squared is 16. 16 to the 1/3, that'd be the cube root of 16 in radical form. And the cube root of 16 is roughly 2.52 if you were to look at the decimal form of that, which, okay, I'll know roughly where to position that point and that local max. Here's the exact coordinate. And then we're going to have 2 local mins. Okay, so if x is negative 2, and we plug that into g, we're going to have 0 coming out of that. So negative 2, 0 would be a local min. And then if x is 2, we're also going to have 0 coming out of that. So 2, 0 would be another local min. And I've plotted those 2 points. Okay. Local max means that we're going to have a hill at that spot. and local min means that we're going to have a valley here at 2, 0 and negative 2, 0. Okay, now you'll notice that in this picture I've made sharp turns. How did I know to do that? How did I know to, that like this max is going to be a nice smooth turn and these mins are going to be sharp turns? Well, it's because the critical numbers 2 and negative 2 are not in the domain of G prime. They're in the domain of G, right? But 2 and negative 2 are a problem for the derivative. So, because I know I can't divide by 0. So I know that I would be not differentiable at x equal 2 and x equal negative 2. Therefore, I'm going to have a sharp turn at those two spots. Okay, and that's something I could have recognized early on here. Hey, 2 and negative 2 caused a problem in the denominator, so these critical numbers are going to produce sharp turns on the graph when I go to find the local extrema. Okay, let's take a look at, here's another example. Okay, find the local extrema for f of x equal x divided by x cubed minus 1. Okay. Well, we're going to use the increasing and decreasing test again. So let's calculate our derivative. There's going to be a quotient rule. Bottom is x cubed minus 1 times the derivative of the top, that's 1, minus the top, that's x, times the derivative of the bottom, that'd be 3x squared, all over the denominator squared. Simplify that. X cubed minus 3x cubed is negative 2x cubed, and then we're going to still have a minus 1 there. Okay, and then I'll set that equal to 0 in order to get my critical numbers. If you multiply both sides by the denominator, that'll clear out the fractional form. Negative 2x cubed minus 1 equals 0. If you add 1 and divide by negative 2, and then take the cubed root of both sides to get x all alone, x would be equal to the cubed root of negative 1/2. Cubed root of negative 1 is negative 1, and so you'd get x equal negative 1 divided by the cubed root of 2, which would be roughly negative 0.79 if you were to look at the decimal form. Okay, now is that my only critical number? Because 1 is a problem here, right, for the derivative? But 1 was not in the domain of the function. Okay, you're only going to have a critical number if x was in the domain. 1 is not in the domain of f. Okay, so negative 1 divided by the cubed root of 2 is the only critical number since 1 is not in the domain of f. Okay, but we know that since x equal 1 is a problem for f of x, we're going to have a vertical asymptote on this graph, right? In general, you're going to have vertical asymptotes on the graph of a rational function for any numbers that you're throwing away as a result of division by 0. Now, because 1 is still an interesting value here in this problem, when I use the increasing and decreasing test, I want to make sure I position 1 on the number line. In general, when you're using the increasing and decreasing test and you make this chart, you're going to include all the critical numbers and any additional numbers that would be creating vertical asymptotes on the graph. All right, now some students won't do that, and that's a mistake because it could lead to incorrect conclusions here as far as increasing and decreasing. Okay, so I'd want to make sure I include 1 on the number line also, because although I don't have a local min or a local max at 1, I've got a vertical asymptote, I still like to know what's happening around 1, okay, whether we're increasing or decreasing. And so I have set up my 3 intervals here, splitting up this number line into 3 groups. And, okay, I need a number in the first group. Negative 1 over the cubed root of 2, that's roughly negative 0.79. Okay, so if you use negative 1, that would be in the first group. Plug negative 1 into the function. You're going to have negative 1 divided by negative 2. Let's see here, I'm in the wrong spot. Plug it into f prime. Negative 1 times negative 2 is 2, minus 1 is 1, and then negative 2 squared is 4. Okay, so 1/4 would be the output. The value of f prime is a positive. That means that we're increasing on that part of the graph. Now I need a number between negative 1 over the cubed root of 2 and 1. 0 would be a good number here because if I plug 0 into the derivative, I'm going to get negative 1 over 1 as negative 1. We're going to be decreasing. And if I use 2 in the last group, plug that in, I'm going to have 2 cubed is 8 times negative 2 is negative 16 minus 1 is negative 17 in the numerator. 2 cubed is 8 minus 1 is 7. 7 squared is 49 in the denominator. That's a negative, so we're going to be back decreasing again. Okay, I'm increasing and then decreasing. That means I'm going to have a local max when x is negative 1 over the cubed root of 2. If you plug negative 1 over the cubed root of 2 into the function to get the y value, I've done that, then, all right, negative 1 over the cubed root of 2 cubed would be negative 1/2 minus 1 is negative 3/2. If you flip that, and of course negative over negative is positive, you're going to get 2 divided by 3 times the cubed root of 2, which in decimal form would be roughly 0.53. Okay, and here's the exact coordinates of that local max. So if I were to sketch a graph now, I know I have a vertical asymptote at x equal 1. Also, I'm going to have a horizontal asymptote at y equals 0, right? Because the degree of the top is less than the degree of the bottom. Whenever the degree of the top is less than the degree of the bottom, your y equals 0 is always a horizontal asymptote. And now if x is 0, y is 0, so 0, 0 would be on the graph. Okay, and we have a local max at the point which would be roughly negative 0.79, 0.53. Okay, and so that's that point there. Now the fact that that's a max means I want to make a hill at that spot. Okay, and I've got an asymptote here, so of course the curve is going to be approaching the asymptote on the left. It'll cross through the x-axis. We're decreasing until we get to 1. Okay, I wouldn't be making a min or anything like that, right? Because that didn't come up in the chart. I'm decreasing until I get to 1. So the curve is going to be heading downward. I'm decreasing after 1. So if I were to just select a value and plot another point here, like if x is 2, plug that in the function. 2 divided by 7, 2/7 would be the output. So here's 2/2, and the curve is going to be falling. Of course, I got to work with these two boundaries here, right? So the curve is going to be to the right of the vertical asymptote, pulling away from that, and then it's going to be approaching the horizontal asymptote from above it. Okay, and so that would be just kind of a quick sketch of the graph of f of x there. Okay. In the next video, I'm going to talk about the concave up and concave down, and we'll look at the concavity test there.